Okay, let's unpack this. Have you ever walked outside and just felt like the world was buzzing with some kind of secret conversation, but you couldn't tune in?
Oh, absolutely.
We think of our senses as these human superpowers, right? But when it comes to the actual spectrum of sound, we're basically deaf to most of what's happening.
It's so true. We're sort of stuck in this narrow little auditory band. It's like having an old vintage radio that only picks up AM.
Yeah.
Meanwhile, the rest of the animal kingdom is on these, sophisticated fiber optic channels, listening and communicating on frequencies we can't even begin to detect.
So that's our mission in this deep dive. First, we're going to get into the specific physical mechanics. We're talking bone stiffness, fluid dynamics, all the molecular stuff
Yeah.
that sets that absolute ceiling for the human ear at 20,000 hertz.
On 20 kilohertz, yeah.
Right, 20 kilohertz.
And for the second part, we are going to cross that threshold. We're going to explore how animals from, a huge dolphin all the way down to a tiny moth evolve these biological cheat codes.
G codes, I like that.
They shatter our limitations and let them operate in the world of ultrasound.
So this deep dive is for you, the learner, if you want to understand the physical blueprints of hearing. Not just what we hear, but why we hear it, and what fascinating evolutionary battles are happening just out of our range. So let's start by defining our own limits.
Okay, so we always hear that standard human range,
Yeah.
right? 20 hertz, which is like a low tectonic rumble,
Right.
all the way up to 20 kilohertz, a really high piercing whine. But that 20 kilohertz, that's really a theoretical maximum. For a young person, perfect hearing.
So if you're an adult listening to this, your mileage may vary.
Your mileage is definitely varied. Your practical upper limit has already dropped.
Yeah.
You're probably peaking somewhere between 15,000 and 17,000 hertz.
And I've heard that under perfect lab conditions, some people can hear way higher.
Some can, yes, maybe up to 28 kilohertz in very rare cases.
Yeah.
But the sensitivity just plummets. And this isn't a flaw in our design,
Yeah.
It's actually an evolutionary compromise.
Compromise. What are we giving up?
Well, we're giving up breadth for focus. Our hearing isn't optimized for hearing everything. It's optimized for survival and communication.
Okay.
If you look at the data, our auditory system is most sensitive. So it requires the least amount of energy to perceive a sound in the range of about 2,000 to 5,000 hertz.
And that number is important because...
Because that is precisely the sweet spot for the fundamental frequencies of human speech.
Yeah.
And maybe even more critically from a survival standpoint, it's the frequency range of a baby's cry.
So evolution basically said, let's focus on understanding each other and keeping the kids alive.
Exactly. Prioritizing that over, say, hearing a distant bat just gave us a way better return on investment.
And before sound even gets to the really delicate parts of the ear, it has to pass through a sort of mechanical filter, right, in the middle ear?
The middle ear, yeah. That's where you find the ossicles, the malleus and corticus and stapes, those tiny, tiny bones.
The smallest bones in the body.
Right. And that whole assembly acts like a mechanical transformer. What's fascinating is that it's a perfect filter. At really low frequencies, the whole system is dominated by stiffness. It resists movement.
Okay, so it doesn't want to move for low rumbles.
And at very high frequencies, the system is dominated by the mass of those little bones, which, resist being accelerated that quickly.
So it finds its sweet spot somewhere in the middle.
It does. The mechanical resonance peaks around 0.8 to 1.2 kilohertz, super efficient. And on top of that, the ear canal itself is an acoustic resonator, and it naturally boosts sounds right around 2 to 4 kilohertz.
Which is speech again.
Speech again. It's a physical advantage, basically engineered to enhance the sounds we need most.
But this amazing optimization, it has a downside, doesn't it? The age-related decline. Why do we lose the high frequencies first?
It's a process called presbycusis, and it really just comes down to wear and tear. The tiny sensory hair cells that detect high frequencies are at the very base of the cochlea, the entrance.
So they get hit with everything first.
They get hit with everything first and with the most force. Over time, they just die off. And because we don't replace them, your upper limit it slowly drops.
Wow. That structural problem leads us perfectly into the core of it all then. The biological hard stop deep inside the inner ear, the cochlear system.
This is where the physics literally defines our reality. Inside the cochlea, you have the basilar membrane.
Yeah.
This is what maps all the incoming sound frequencies.
This is the tonotopic organization.
Exactly. And the best analogy is to think of it like a highly specialized, tapered xylophone.
A xylophone. Okay, I can picture that. But if the whole thing can vibrate, What physically stops it from responding to frequencies higher than 20 kilohertz?
It's purely mechanical. It's all about the membrane structure.
Mm.
At one end, the apex, it's wide and floppy. That part resonates with low frequencies, like a big, slow bass drum.
Right.
At the other end, the base, right near the entrance, it's narrow and very, very stiff. That's for the high frequencies, like a taut snare drum.
So frequencies above 20 kilohertz are just too fast,
Yeah.
too high-pitched for even the stiffest part.
They just can't create an effective ripple. The stiffness and the physical dimensions of our human membrane mean those ultra-high frequencies can't physically displace it enough to create a signal. It just fizzles out.
Okay, so the sound wave travels down the xylophone, it finds its spot, and then the hair cells, the stereocilia, they turn that vibration into a neural signal. But you mentioned there are different kinds of hair cells.
Yes, and that's a crucial distinction. You have inner hair cells, the IHCs, and outer hair cells, the OHCs. The inner ones are the true reporters. They sense the velocity of the membrane and send the final signal to the brain.
And the outer hair cells, what do they do?
They're the amplifiers. They're really sensitive to displacement, and they provide this amazing boost. They sharpen the tuning and increase sensitivity, especially for quiet sounds.
Okay, so here's the big question. What frequency are those cells tuned to?
This is the key technical fact. If you compute the resonant frequencies of that whole hair cell system, our cochlear map, it ranges from about 1.2 kilohertz at the floppy end to around 22 kilohertz at the stiff end.
A near perfect match for our maximum hearing range.
Exactly. The limit isn't in our brain. The physical machinery itself cannot convert or transduce those higher frequencies. It's a physical wall.
So we didn't evolve past that point because it was just too costly, making the membrane even stiffer.
Probably too costly, or it just offered diminishing returns for our survival needs.
Which takes us to the really fun part. If we're so physically constrained, how are other animals just smashing through that 22 kilohertz ceiling? We're now heading into the ultrasonic world.
We are crossing the threshold into systems built for, well, for speed and precision. And the kings of this domain have to be the echolocating masters,
We're talking about bats.
starting with bats.
They're basically using sound like an auditory flashlight, right? Emitting calls from 20 kilohertz all the way up to what?
All the way up to 200 kilohertz. Some species can even hit 212 kilohertz. And they are loud. I mean, some of their calls are 120 decibels. That's louder than a jackhammer right next to you.
Why so high? Why do they need that kind of frequency? Wouldn't a lower frequency travel farther?
Yeah, but you'd lose all the detail. The shorter the wavelength, which means a higher frequency, the more detailed the information you get back. It's like switching your TV from standard def to 4K.
So they can see the tiny details on an insect's wings.
Exactly. Its size, its range, its subtle movements. You need high frequency for that kind of resolution.
And that same need for high-res navigation is even more critical underwater, where you can't see anything. So dolphins and toothed whales.
Dolphins can detect frequencies up to 150, maybe 160 kilohertz. And because sound travels about 4.5 times faster in water, acoustics is really the only reliable way to see your world.
And their precision is just legendary.
It's unbelievable. They can reportedly tell the difference between two objects the size of a marble from a distance.
Wow.
But you don't even have to go to the ocean or the night sky. Your house is probably full of ultrasonic listeners.
You mean our pets, our furry listeners. I know my dog can hear a dog whistle. I can't, so that's, what, 45 kilohertz?
Up to 45 kilohertz for dogs, yeah. But your cat is an even better hunter. Cats can hear up to 79 kilohertz.
And there's a good reason for that, isn't there?
A vital reason. Their favorite prey mice, rats, they communicate almost entirely in ultrasound.
They're on a private channel we can't hack into.
A completely private channel. Mice use 22 kilohertz signals for, danger or stay away, and 50 kilohertz signals for pleasure and reward. They're having complex social interactions that we are completely oblivious to.
Okay, but now for the absolute champion of this ultrasonic arms race, the moth.
The greater wax moth, Galleria melanella. This little thing is it's a record holder.
It has the highest frequency sensitivity of any animal, right?
The highest known. It can approach an astounding 300 kilohertz.
300? That's 15 times higher than my absolute best hearing. Why on earth would a moth need that?
It's 100% a defensive adaptation against its number one predator, the bat.
An early warning system.
The perfect early warning system. The moth has a special organ that can detect the bat's high-frequency echolocation call before that sound wave even hits the moth and bounces back to the bat. It gives it just a few precious milliseconds to take evasive action.
So the moth is listening in on the bat's sonar.
And diving for cover before it even shows up on the radar.
That's incredible. But
Yeah.
it brings us to the ultimate question. How do they physically do it? What are the cheat codes that let them hear at 300 kilohertz when we hit a wall at 22?
Well, the cheat codes are all about radical modifications to the very same structures that limit us. It starts, again, with the basilar membrane.
So it's just stiffer.
It is, but it's extremely specialized. In an animal like a mouse, for instance, the whole membrane is engineered to have its best frequency response peak around 48 kilohertz.
Double our maximum.
The entire structure is built for speed.
Which means the hair cells have to be fundamentally different too, on a molecular level.
They need a serious molecular upgrade. These cells have to respond to tiny, tiny movements, sometimes just 50 to 100 nanometers. So research has pointed to specialized high-speed ion channels, like one called PGO2,
So like a faster sensor.
and an ultra-fast, ultra-sensitive mechanical sensor. It can open and close almost instantaneously to register the rapid pressure changes of ultrasound, something our slower channels just can't keep up with.
And what about the bats themselves, the apex predators of this whole soundscape?
The architecture of a bat's outer hair cells is it's radically different. They have these distinct shapes. Some are flask-shaped, others are ball-shaped. And these aren't random. They're mechanical enhancements, acting like tiny resonators to amplify and transmit high-frequency sound with maximum efficiency.
So it's not just one thing, it's the membrane, the hair cells. But the brain has to be able to process all this high-speed data.
And that requires a major brain power upgrade. Echolocating animals have auditory cortices that are dramatically larger than ours, proportionally. They dedicate way more neural real estate to sound.
But it's not just bigger, is it?
No, it's smarter. They have these specialized units called combination-sensitive neurons.
So they don't just hear a sound, they hear a relationship between sounds.
Precisely. These neurons will only fire in response to a specific combination of frequency and timing. This is the genius of the system. It lets the bat's brain distinguish between its own deafening outgoing shout.
And the faint little echo that comes back.
Exactly. And from that tiny difference, it can instantly calculate the target's location, its speed, its direction, all without being overwhelmed by its own noise.
It really makes our own hearing feel, robust for our niche, but totally deaf to this whole other layer of reality.
That's a perfect way to put it. Let's distill the core insights from this deep dive.
Okay, key takeaway 1. Our human hearing range, maxing out around 20 kilohertz, is an evolutionary compromise. It's finely tuned with maximum sensitivity between 2 and 5 kilohertz to prioritize human speech and survival sounds.
Key takeaway 2. Our limits are physical hard stops. It comes down to the mechanics, the stiffness of the middle ear, and the unchangeable physical properties of our basilar membrane and our hair cells. The hardware simply isn't built to vibrate any faster.
And key takeaway 3, the animal world uses ultrasound as this vital survival channel, and it's enabled by incredible specialized structures. Everything from a moth's special organ to a bat's molecularly upgraded hair cells. Every creature has its own biologically engineered reality filter.
Our silence is their communication channel.
And here's where it gets really interesting. If you think about the sheer volume of that ultrasonic chatter going on all the time, bats hunting, mice signaling pleasure and danger, insects fighting for their lives, we are surrounded by these rich, constant biological conversations we just can't perceive.
A whole other world.
So here's the thought. If we could suddenly shift our ears above that 20 kilohertz limit, what complex secret societal details of the natural world would we discover that are currently hidden from us? Something for you to chew on until our next deep dive.